Welcome back to an introduction to the Discrete Fourier Transform. In this lecture, we'll talk about a simple application of the Discrete Fourier Transform noise filtering. So I created a sound file that has a recording of a trumpet sound plus some generated high frequency noise. So this lecture kind of walked through the assignment, which is to use Python to filter out that noise. Okay, so as before, we're going to input all those libraries that we need. And then we're going to read in this this file, which is the trumpet chirp file. So the wave file, we've seen this before in the previous video. This wave file read function will return the sampling rate and the data from the wave file. So this is called trumpet chirp. And then we can create an audio object that plays the file. So you notice it's a recording of a trumpet plus some really annoying high frequency noise. So in the previous video we talked about this function, the plot signal frequency function that takes the digital data and allows you to specify the range of frequency that you want to look at. And this function will graph the frequency domain of the sound. So let's run this, and then we're gonna call it to on the data that we have, and we'll just look at from 0 to 10,000. So in this range from 0 to 10,000, notice that we have here the high frequency noise that I generated, and here's all the harmonics of the trumpet sound. So the assignment for this is to filter out this noise, and you kind of see how this works. The original sound is in the time domain, which it's hard to work with. So we convert this to the Fourier coefficient, which has all the harmonics and all the frequency information, and we simply zero out, make all this zero, and then we just use the inverse Fourier transform and convert back to the domain representation, and then there we have a sound that doesn't have that noise. So it's kind of amazing how that works with the discrete Fourier transform make this so easy to take out a certain sound that we don't want. Let's just plot this again and zoom in. So we're going to look at from 6,900 Hertz to 8,000 and see that this is basically that noise that we heard. Okay, so in this problem, up to now we've been using the FFT.FFT function, but now in this problem it's actually easier to use the RFFT. We learned from the previous lecture that every view signal has a symmetric spectrum, and so the RFFT simply ignore the second symmetric half. This makes it easier for us when we do the inverse transform. We don't have any complex number artifacts, and so the RFFT only consider the frequencies up to the Nyquist frequency. And so let's take a look at the difference. So if I were to create up to now we've been using this function. Take our sample, convert it into the complex version of the Fourier coefficient. But now we want to do the same thing, except that we want to create it for using the RFFT. So if I had to do that, I'll call this real. And if I were to print out, for example, the size of the list of coefficient, then I notice that the FFT gives you all 100,000 sample, but this one only gives you half of it. So because it ignores the second symmetric half. And so we've done this before, where we were able to plot the frequency information of a sound. So I'm gonna just run this, and notice that as we know, if I use the complex version, the FFT version, then I get the symmetric spectrum. So every wave signal has this property that whatever frequency I have the symmetric negative half of it. And so notice that if I were to do the same thing for using the RFFT, which is the real coefficient only, when I graph this, then I get that the second half is ignore. So the RFFT simply look at the first half. And so the assignment will allow you to walk through that process of filtering out the noise, but one thing that you might need is that Numpy array has slicing capabilities that allow us to access and manipulate the array. So I want to kind of give you a quick example of how that works, and this will help you with the assignment. So if I were to create an array, a Numpy array, so here's what slicing does. I can access from the beginning index to an ending index, and this will go from 1 to 4, so it doesn't include the last one. If I were to print that out, it gives you starting at index 1 all the way to index 4. So this is slicing. I use a colon for that. And I can also slice from, if I don't specify a number, then the first number, then it will start at the beginning. So for example, if I were to do this, then it will print out from beginning up to and not including 3. In the same way, if I were to do, if I don't include the ending number, then it will go all the way to the end. If I do that, then it will go from 2 all the way to the end. And lastly, if I don't specify the beginning nor the end, then it'll go from the if I don't specify the first or the last index, then it'll just go from the beginning to the end. And another thing that is nice is that if I want to manipulate a certain subset or sublist of this array, I can use slicing. So for example, if I want to say from 1 to 4, and say access all those numbers and make them all 0. So this is very nice. This is actually very easy. In Java, this will require a loop, but in Numpy array, we can do this. And notice that if I to look at all the numbers from 1 to 3, make them all 0, and that's what happens. When I print out A again, all those numbers are 0 out. So that will help you with that assignment. Okay, thank you for watching.